to continue looking at problems. In the last unit, we looked at applying strategies to relatively straightforward problems. This time we're going to look at problems that are possibly a bit more complex. We're going to look at word problems. First, let's review the strategy that it takes to solve a word problem. First, we gather information, read it carefully, and try to see what's given to us and what's asked. We try to visualize this with some kind of a sketch that includes that information. We write down an analysis, steps to solve the word problem, perhaps formulas if they're relevant. We then solve the problem numerically, including, of course, the units or what the result refers to, and then we check by putting our answer back into the equation or formula, or check for reasonableness. Let's start by looking at some problems. We'll start with some fairly easy ones first, and then work our way up. Brad found an apartment that rents for $275 a month. He plans to live there for 2 years, and we would like to know how much he spent for rent at the end of the 2 years. So let's look carefully for the information given there. He spends $275 a month on an apartment, and he plans to live there 2 years. How much will he have to spend at the end of 2 years? Let's gather the information and summarize it. We're given $275 a month, pretty cheap rent. He pays the rent for 2 years. If I were paying that, I'd stay in that place too. And we know we have to bring in from our own knowledge that there are 12 months in a year. And we want to know what the total is for 2 years' rent. So we multiply the 12 months per year by the 2 years to get the total number of months he pays rent for. Then we multiply that number by 275 to find out how much he spends in 2 years. Let's work it out. 12 months times 2 years is 24 months. Then we take the $275 per month, multiply that by 24 to get $6,600. So Brad pays $6,600 in rent over a 2-year period. Let's look at another problem. Again, we're starting off in a fairly straightforward way and then looking at problems that are more and more complicated. In 1990, there were approximately 31 times as many people living in Texas as there were living in Alaska. If there were 551,947 people living in Alaska at that time, how many people were living in Texas? Let's see what we're given and what's asked. There were 31 times as many people living in Texas as living in Alaska. We're given how many people were living in Alaska, and we want to know how many people are living in Texas. Let's summarize the information. There are the number of people living in Alaska, 551,947. We know that the number of people in Texas is 31 times that living in Alaska, and we want to know how many people are in Texas. Let's summarize that and look for an analysis of what we need to do. So we need to multiply 31 times the number of people in Alaska to get the number of people in Texas. Let's solve it. 551,947 times 31. We work this out, and we see that we have 17,110,357, and we need to indicate the complete answer is 17,110,357 people in Texas. Here's another one. A newspaper person delivers 400 papers every day. On a typical day, she delivers 87 to a townhouse complex, 134 to houses on the east side and sells the rest of the newspapers from a booth. And what we would like to know in this problem is how many papers are sold from the booth. Let's examine it for information. 400 papers a day, 87 to the townhouse, 134 to houses on the east side, and we would like to know how many are sold from the booth. Summarize the information. What's asked for? We want to know the papers sold at the booth, and we can call that B for booth. We could call it XYZ, but we're calling it B for booth. It makes it easy when we solve it to know what we're looking for. What information are we given? 400 total, 134 to the east side, 87 to the townhouse, and how can we visualize this? I think of all the papers as a big box, a quantity, and we know that quantity is divided various different ways. 87 go to the townhouse, 134 go to the east side, and what we're looking for is how many are sold at the booth. Let's analyze this. The total, which indicates addition, must be 400. So the number sold at the townhouses plus the number sold at the east side plus the number we want to find, the number sold at the booth, is 400. Let's work on the solution. We can write this out as an equation, 87 plus 134 plus B equals 400, and we need to solve this equation for B. We can see on the left that the 87 and 134 are just numbers, so we might as well add those numbers together to get 221 plus B equals 400. Again, the point of solving the equation is to get B by itself. So we think of our balance and we subtract 221 from the left and right side of that equation, and we wind up with the solution that B is equal to 179. But then we need to write down the complete answer, which is 179 papers were sold from the booth. To check, all we need to do is plug in our value for B and see if those three numbers in fact add to 400, which we see that they do. Let's look at another problem. This is a number problem, which is just a statement about the numbers that we need to find what the numbers are being talked about. Two consecutive numbers have a sum of 91. What are the numbers? Pure information. Two consecutive numbers, you add them together, you get 91. What are the numbers? Let's gather the information. We have two numbers. The sum is 91. And the question is, if we have two consecutive numbers, let's call the first number n. Consecutive means it's either right before it or right after it. We'll talk about the number right after it. That's got to be one more than n or n plus 1. And we want to know what those numbers are. Let's try to visualize what's happening. So I write out numbers. Start with 1, 2, 3, 4, comma, a bunch of numbers in between. 34, 35, comma, a bunch of numbers in between. We don't know what the numbers are, but somewhere in that line of numbers is n, the first number, and n plus 1, the next consecutive number. So here's n, our number. Then here's the next consecutive number, n plus 1. And to analyze it, we know that the sum means addition, and we know that the number plus the next number in line is 91. We can now express this as an equation, n plus the quantity, n plus 1 is equal to 91. Now we know with addition, the location of the brackets won't make any difference on the sum, so we can just remove the brackets and get n plus 1 is equal to 91. N plus n is 2n, so we wind up with the equation based on our analysis that 2n plus 1 equals 91. We now need to work on the solution to the equation. We have 2n plus 1 equals 91, we need n by itself. So I subtract a 1 from each side of the equation to get rid of the 1 on the 2n side, and I'm left with 2n equals 90. Then I need to divide both sides of the equation by 2 to get n by itself. When I do this, I wind up with n equals 45. But I'm not done because the question asks for two consecutive numbers. N is the first number, n plus 1 is the second number. So the two numbers we found are 45 and 46. The last thing we need to do is check our answer. Is this reasonable? And we know that the sum of those two numbers have to be 91. So we can add them together, and we find, in fact, 45 plus 46 is 91. So we can be very, very sure that we've answered this problem correctly. Let's look at another one. Determined to win a pie eating contest, Homer Simpson went into training. This is some training. Each day for 6 days, he ate 4 more pies than the day before, for a total of 150 pies. How many pies did he eat each day? So let's look at the information we're given. There are 6 days, and he ate 4 more pies each day than the day before, for a total of 150. We're asked, how many pies did Homer eat each day? So let's gather the information and summarize it. We'll say that n is the number of pies Homer ate on the first day, then n plus 4 the second day, 4 more than that is n plus 8, and so forth for each of the succeeding days. And the total number we also know is 150. How many pies did Homer eat each day? So we need to analyze this. We write an expression for the number of pies Homer ate each day in terms of the n pies and add them together and set them equal to 150. Then we solve for n, and from there we can find out how many pies were eaten after the first day. We'll add up all of the pies that were eaten, n for the first day, 4 more for the second, 4 more than that for the third, and so forth. When we add these together, we can add the n's and the numbers separately, so we get 6n plus 60. We know that must be 150. We have our equation, and now we can continue to solve the equation for n. We see that on the left we have a 60, so that what we must do is subtract 60 from each side, leaving us with 6n equals 90. To get n by itself, we divide both sides by 6. When we do that, 90 divided by 6 is 15. So on the first day, Homer ate 15 pies. We'll continue with the solution because we need to know how many pies Homer ate on all 6 days. So on the first day, 15 pies. Day 2 is 4 more, 19, 23, 27, 31, 35. So here are all of the pies that Homer ate on each of the 6 days. How can we check this? Well, we can add up all of these pies and find that they, in fact, add to 150. So that we can be pretty sure that this solution is the correct one, since if we take the number of pies Homer ate on each day and it adds to 150, that's pretty good verification. Let's look at yet another problem. And this one's a little bit different because it doesn't ask for any formulas, but it asks us to apply the rounding procedure that we looked at earlier in this class. Ed and Terry both rounded the number 34,682. Now remember, you can round this to various places, and Ed found the places which would allow him to round the number up, to round it to a value greater than the 34,682. Terry rounded the number down, which meant that he looked for places that would round the number so that the value of the rounded number was less than the original value. Assuming that both followed the rules for rounding, to what places might the number have been rounded by Ed, who rounded the number up, or by Terry, who rounded the number down? Let's gather the information and summarize it. So we're given that the number is 34,682 and that both men followed the rules for rounding. And the question is, if Ed rounded the number up, what places would he have rounded that from to get a larger number? If Terry rounded the number down, which places must he have rounded that from to get a smaller number? Let's try to visualize this. So there's the 34,682, and under what circumstances would you round that to make a larger number? Under what circumstances would you round that to make a smaller number? Which of the places would you round from to get the larger number? Which of the places would you round from to get a smaller number? Let's analyze this. The first thing we need to remember are the rules for rounding. If you pick a place, you put your finger on that place, for example, the hundreds place, and then check to see whether the numbers to the right of it are greater than or less than 5. If they're greater than equal to 5, you round up. You make the number you have your finger on one more and put zeros to the right. If the numbers to the right of the one you have your finger on are less than 5, you leave that number your finger is on the same and just put zeros to the right. So we round 34,682 correctly to each possible place, and those solutions that get rounded to a larger number are for Ed. Those solutions that get rounded to a smaller number, get rounded down, are solutions for Terry. Let's round that number to each possible decimal place. Let's round it first to the nearest 10. So I would put my finger on the 8 and look to the 2 at the right. That's less than a 5, so I would round that down, and the rounded down value would be 34,680. Next, I put my finger on the 6 on the 100, look to the right, I see an 8, so I change the 6 to a 7, put zeros in after that. Then I would look to the nearest 1,000, put my finger on the 4. I see in the hundreds place I have a 6, so I round up. And finally, I put my finger on the 3, round to the nearest 10,000. I see the 1,000 place is a 4, so I would round that down to 30,000. So I've rounded the first one down. The value is less than the original number, so Terry gets that one. I round the next number up. 34,700 is greater than the 34,682. Ed gets that one. To the nearest 1,000, you also round up, so that goes to Ed. And finally, to the nearest 10,000, I've rounded down, so that goes to Terry. To check my answer, all I need to do is compare the original number to my rounded numbers to see if, in fact, the rounded number is less, which means that that was something Terry did, or the rounded number was greater, which was something that Ed did. So I see by the comparisons that my solution is the correct one. Here's another problem, one that lends itself very well to visualization. A swimming pool measures 14 feet by 40 feet, and it has a rectangular deck around it that's 6 feet wide. We'd like to know the area of the deck. Let's look for the information in that. So we're given that the pool is 14 by 40, and it has a rectangular deck around it that's 6 feet wide. Let's summarize that information. So there's the width and length of the pool, 14 by 40, and the width of the decking all the way along is 6 feet. What we would like to get is the area of the pool deck, and we'll call that D. This is a very good problem to make a diagram. So let's try to visualize it. There's the pool, the blue pool, and that's 40 feet by 14 feet. And all around that, we have a deck which is 6 feet on every side. Not to mention the frog. Now let's analyze this and see what steps we must take to find the area of that 6-foot decking. We have the area of the pool, that's the area of the pool decking, that's the area of the green rectangle, and the area of the pool is the blue rectangle. So we need to take the area of the decking then would be the area of the green rectangle minus the area of the blue rectangle. So what's the formula for area of a rectangle? We remember the area is the length times the width, which we can abbreviate algebraically as A is equal to LW, length times width. Let's solve this problem. So we know that the area of the deck has got to be the area of the larger rectangle, which is the pool plus the decking, minus the area of the blue rectangle, which is the pool itself. So we write the equation that the area of the decking is the area of the green minus the area of the blue. But the area is length times width in each case. So the area of the decking is the length of the green rectangle times the width of the green rectangle minus the length of the blue times the width of the blue. So we have that the length and width of the blue rectangle is 40 by 14. Let's work with the solution. We need the length and width of the green rectangle, which is the larger one, and we see that the length of it is the 40 feet plus the 6 feet on each side to make 52 feet, and the width is the 14 feet of the pool plus the 6 feet on each side to make 26 feet. We now have enough information. Again, the area of the decking is the area of the green minus the area of the blue, the length times width of the green minus the length times width of the blue. So we put the numbers in, then we do the multiplications that are indicated, and then the subtraction to find that the area of the decking is 792 square feet. We can check that by seeing that the area of the green rectangle is the area of the decking plus the area of the blue. In other words, if the total area of that whole rectangle is 1,352 square feet, that's got to be equal to the area of the decking, which we calculated as the part of the problem, plus the 560 square feet of the pool. And we see that that does add up, so we can give the frog a big hello, and we've done this problem correctly. I have one more problem for you, and it's a doozy. When Malcolm visited his grandfather's farm, he found they raised only hens and pigs. Malcolm counted 28 heads and 100 feet in the barnyard. How many hens and how many pigs did Grandpa have? Let's take a look at what information is given in this problem. We see that there are 28 heads and 100 feet of the pigs and chickens. So we need to find out, just from that information, knowing we have pigs and chickens, how many of each variety did Grandpa have? Let's gather the information and look at what we're given. We're given the fact that if we count all of the heads of the pigs and the heads of the chicken, we have 28. If we count all of the feet, remember each pig has 4 hopefully, and all of the feet of the hens, they have 2, we'll get a total of 100. And the question is, what is the number of pigs we have? And we'll call that P. And what's the number of hens we have? Call that H. And we know, as I said before, that each animal has 1 head, a pig has 4 feet, and a hen has 2 feet. Let's try to visualize this. Here come the pigs, and we can count pigs' heads, see the 4 feet. Here are the hens walking in backwards. we know that the pig's heads plus the hen's heads, if we count heads, we get 28, and if we count feet, we get 100. Let's analyze this. We know that each animal has one head, so that the pig's heads and the hen heads equals 28. So since there's one head per animal, there are 28 animals all told. So if there are p pigs, the number of chickens must be 28 minus however many pigs there are. And that's going to be useful information. So we say that the number of hens is 28 minus the number of pigs. And we also know that if we count feet, and here we mean literal feet of things, not a length. So we have 100 feet is 4 times the number of pigs, because pigs have 4 feet each, plus 2 times the number of hens. Let's work on the solution. We first use the expression to get the expression for hens in terms of pigs, so we have one unknown to solve the equation. So if we start with 100 feet is 4 per pig and 2 per hen, we can substitute for hens 28 minus p, which is the same. Then if we continue the math with the equation, we use the distributive principle, multiply 2 by everything in that parenthesis to get 100 is 4p plus 56 minus 2p. Then we can combine the 4p and 2p, and we finally wind up with the equation 100 is 56 plus 2p. Now we need to solve the equation. We first eliminate the 56 from both sides of the equation and get that twice p is 44. We want p, the number of pigs, all by itself, so we then divide both sides by 2, and we find out that we have 22 pigs. It's only part of the answer. We need to know how many hens we have. So if we start with 22 pigs, and we know that the number of hens is going to be 28, the total heads, minus the number of pigs, we find out that we have 6 hens. So we have 22 pigs, 6 hens. Let's check that. First of all, we see we have 28 animals. That's correct. So if we multiply 22 times 4 for the number of pigs times 4 feet, and 2 times 6, 6 hens, 2 feet, we see we have 100 feet.